Good morning, students. I am Karkurali, Assistant Professor from EEE Department, RMD Engineering College. Let's move on to the topic.
Today I am going to tell you about the introduction of power system analysis. This is the first unit syllabus where the first half contains the impedance diagram of the power system, and then second unit is having the bus admittance matrix. These two topics are very important in the first unit. And today's agenda is introduction to power system, functions of power system analysis, and need for system planning and operation studies, introduction to single line diagram and its per unit value, and change of base values. And the power system, we know the power system, the major components are generating units and transmission lines and distribution network. These are the three major part which are interconnected together, is nothing but a power system. The meaning of system is nothing but the various components are connected together to perform particular task. If it is a power system, then the power system major components. What are the major components? As I already told, generation units, transmission lines, and distribution network. So the power system generally is used for generating the electrical power, which is supplied to the different generated from different sources and transmitted, and it is distributed to the end consumers. And power system analysis is nothing but evaluation of the power system, is called power system analysis. And some of the functions of power system analysis, that is what is the need, why we go for the power system analysis, nothing but we have to monitor the voltage at various buses. Okay, this is very important to monitor the voltage and real power and reactive power flow between the buses. Why? Because if reactive power increases, so real power requirement for the particular load decreases. If real power decreases, the current consumption by the particular load will be increasing. So in order to avoid these things, it is necessary to monitor the voltage. And the thing is to design circuit breakers also. We need to design circuit breakers. For that we have to understand what's happening in the power system, correct? Then to plan for future expansion. So we have to anticipate what should be the, or what will be the demand in the after 10 years or after 5 years. Based on that we have to plan for the generation unit also. And for that, we have to analyze the power system. So what is the demand for the previous year, and what is the demand for the current year, and what is expected for the next year and the next year, like that, to analyze the system under different fault conditions. So if any fault occurs, what happens to the system, whether the fault is tolerable or not tolerable, or what happens, and we have to analyze this fault will affect other elements connected to this, how to isolate the system or when to isolate the system. So what happened to the system, these things are necessary, correct, when fault occurs. So these are the functions of power system analysis. And what the things, another one is to study the ability of the system for small and large disturbances, which is nothing but comes under the stability analysis. So the functions of power system analysis also include stability analysis. We can say for planning, for stability analysis, and to monitor the voltage at various bus systems are the basic or major functions of the power system analysis. And need for system planning and operation. The system planning is nothing but, I already told, the power demand. The power demand is to be anticipated. Based on that we have to generate the power. So generally the power demand must be equal to sum of the power generation. The fundamental objective of power system planning is to provide uninterrupted power to the consumers. Uninterrupted power to the consumers. These are the major planning of power system. And we'll be planning first, and then we'll implement the plans, and we'll monitor and we'll compare the plans with the result, whether it reaches our target or not. If it is not reaching, we'll do some corrective actions. Again, we'll planning and we'll implement. This is the cycle for power system planning and operation. And the components of power system, I already told there are major components are at the generation side, and then transmission side, and then distribution side. These are the major part. Generation side, we know what is the major component: generator or alternator, because it generates AC, we'll say this as alternator. In here in generation side itself, we will be having the power transformer, correct? It steps up voltage and steps down the current. And then the transmission line. Then distribution side will be having the substation transformers, or we'll say distribution transformers. And the our another thing, major thing, is loads. Okay. Then coming to single line diagram. Single line diagram is the precise representation of the entire components of the power system which are connected in single line. See here, this is a generator, and this is a circuit breaker and bus and transformer. Here we are having the transmission line, again transformer. These components, the major components, are connected with the help of a single line, correct? Hence it is called a single line diagram. So these are the standard symbols for single line diagram. For any rotating machine, circle is used. For 2-winding transformer, for 3-winding transformer, circuit breaker, this is for air circuit breaker. For delta connection, star connection, star with neutral. These are the standard symbols used in SLD, single line diagram. And purpose of using single line diagram, I already told you, the precise information, precise form of significant information about the system is intimated here. And the definition for per unit value. Per unit value is the ratio of actual value by base value. And we have to understand what is the base value and why we go for per unit value, or why we prefer per unit value. And need for base value is given here. The power system components of various sections are operate at different voltage and power levels. So it will be convenient if you have some base value or some common value. Okay, for our convenience only we use the base value, which is nothing but a common value. Then advantages of per unit system. Generally the per unit impedance values will have the narrow range values. Generally they will have a very narrow range. See, they lies in a narrow range. Then if you take per unit impedance of a transformer, this is same in the primary as well as secondary side. But if you take equivalent circuit of the transformer, the primary and the secondary total resistance value are not same. The resistance referred to primary and resistance referred to secondary, they are not same. But in the case of per unit impedance, both are same. So we can take any value. There is no possibility of taking the wrong value. Okay. And generally manufacturers are generally specify the ratings of the equipment in per unit value. And the per unit value calculations are also very simple. It reduces the complexity, and these per unit systems are ideal for the computerized analysis and for simulation of complex power system also. So as I already told, for even for a transformer, the per unit calculation for both star and delta connected networks are same. And this is the per unit formula. So if given values in single line diagram, if the given values, reactance values or impedance values are given in per unit, then if we are going to find out new per unit value, means this is the formula. new per unit impedance is equal to old per unit impedance multiplied by old base voltage divided by new base voltage whole square multiplied by new base power divided by old base power. So if the reactances or impedances are in ohms, okay, if they are given in ohms itself, then to find out new per unit impedance, then we will use this formula, Z multiplied by, this comes from generally Z divided by Z actual divided by Z base. Okay, we know the power formula, P is equal to V square by Z. From this I can find out the Z value, correct? What is the Z value? Z is equal to V square divided by P. Okay, so I want to convert this into kilovolt, or I want to convert this into mega volt ampere. So what I have to do, I have to multiply both side by 10 power, that is in both numerator as well as the denominator. I have to substitute 10 power 6, and in denominator also 10 power 6. So what happens, if you consolidate this, you will get kilovolt the whole square, correct, because 10 power 3, no, so 10 power 3 can be converted into kilovolt, and if you put square, then it will have 10 power 6 in the numerator, and then in denominator 10 power 6, no, shall we put this as MVA, megavolt ampere, MVA. Okay, this is the impedance formula, correct? Now this is the impedance formula. Now if you substitute base here, base impedance, what you will write? MVAB, correct, base power and base voltage. This one only is substituted in the formula Z divided by Z per unit. What is Z per unit? Per unit is nothing but actual by base. So Z is the actual value divided by Z base, actual divided by base value. If you substitute base value here, what is the formula? K, base voltage square divided by base power. If you substitute here, you will get this formula. Okay, so these are the basic things we have to understand. Once you remember the formula, it's very easy for you to solve the problems. Then our aim is to draw impedance and reactance diagram, correct? So in impedance diagram, the components are represented by the impedances or reactances. If Z is equal to R, we know R plus Jx, correct? R plus Jx. If resistance is not there, then impedance is represented by the reactance only, correct? Impedance is equal to reactance. So various components are represented by the equivalent impedance. It is used for load flow analysis, and then the approximation made here is neutral reactance are neglected and shunt branches of the equivalent circuit of transformers are neglected. Then in reactance diagram, here only reactance, not impedance. There in impedance diagram, impedances are represented. Here reactances are represented for each component. This is used for fault calculations, and neutral reactance are like the previous impedance diagram. Here also neglected, here also shunt branches are neglected. The only thing apart from impedance diagram, we are neglecting the resistance, we are neglecting the static loads, and capacitance of the transmission lines are neglected. Even in impedance diagram, capacitance of the transmission lines are neglected. Now we will discuss how to draw the impedance diagram for the given single line diagram. See, now let us check first how many components are there first. See, first we are having a generator. We are having a generator here, and we are having a transformer, and in between we are having a transmission line, and then here another transformer, and then here we are having the motor. So totally we are having the 5 components. For these 5 components, we have to draw the equivalent impedance. Okay, so as we know already, see here, this is the equivalent circuit for generator. This is the equivalent circuit of generator. The only the current flow direction is different for generator and motor. See, this is the equivalent circuit for motor. See here, the rotating armature is represented by the circle and its resistance and reactance. In the case of generator, the same manner it will be in the motor, but the difference is current direction will be different. So now we have the equivalent circuit for generator as well as motor. Then for transformer, this what we have studied earlier. This is the equivalent circuit for the transformer, correct? You know it already. This is the equivalent circuit for the transformer. So this is the shunt branch and this is the primary side and secondary referred to primary, correct? Then the third component is transmission line. For this transmission line we are having two modeling. One is pi, another one is T type. So generally for a long transmission line it's preferred for pi. Okay, so this is the equivalent circuit for the transmission line, correct? This is the third one. Then fourth one, transformer. Again we know the transformer equivalent circuit is this one. Okay, now the last component is motor. I already told it is similar to the generator, only thing the current direction will be different. So like this we have to combine now all the components. See here, generator is connected with the transformer like this, with the transformer like this. Okay, then after transformer, transmission line will be connected like this. Then after transmission line it is connected to the transformer like this. See, it will be connected like this. After transformer 2 it will be connected to the motor like this, right? Now this is the equivalent impedance diagram for the given single line diagram. But in impedance diagram what we have taken, all the shunt branches are neglected. So we can neglect all the shunt branches. This is first equivalent circuit, correct? Then what I am doing, I am neglecting all the shunt branches. So I will get like this only. Okay, now this is the, let us have this as the equivalent circuit. Now I will emphasize here what are the things. See, this is for generator, correct? Now this is for transformer 1, this is for transmission line, and this is for transformer 2, and this is for motor. Okay, when shunt branches are neglected, if these two are in series, what happens, we can combine the resistance and reactance. R01 and R02 can be, correct, both can be combined here. Resistance and reactance can be combined. If you combine this, now what will get, only single reactance and single resistance will be there, correct? So I can remove this one because I'm going to represent, I'm combining these two together, so I'm going to represent with a single resistance and reactance for a transformer. So it will be like this. Okay, same manner I can eliminate here also, because transformer primary and secondary values are connected in series, hence I'm connecting the, I'm using only a single resistor and reactor. Now these are the final equivalent impedance diagram. Okay, now this is impedance diagram. Now if you take reactance diagram, what is a reactance diagram? Reactance diagram. In reactance diagram, all the resistances are neglected, correct? So if the resistance are neglected, how it will be? See, this can be removed and this resistance in the transformer can be removed. So because it doesn't have resistor, correct? So this resistance can be removed, this resistance can be removed. So the final diagram will be like this only. This is the reactance diagram, correct? See, this is the reactance diagram. So it doesn't have any reactances, simply, sorry, it doesn't have any resistance, it simply have only the reactances. So now this diagram becomes a reactance diagram for the given single line diagram. Okay, thank you all.